What are the 5 factors that you can change to change the rate? Okay, what are the 5 factors that you can change to change the rate? So tell your neighbor.
Like volume, temperature, surface area. I go back to my notes. Notes, it's not the notes volume, temperature, surface area. There's 2 more. Think about speed. Oh yeah, speed. Yeah. No, speed is dropping on color. How that makes sense. I believe in theory. Catalyst. Concentration. Yeah, concentration. Pressure, volume, temperature. Pressure, I guess. Wait. Yes, I'm not gonna be part of it. No, you should be more. I saw my name go in the middle and I was like, no.
You're like, yes.
I should be.
Okay, I'm going to draw a name. Remember, if you get drawn and you don't want to talk to me, that's okay. You can just say pass, all right? So I'm going to ask for one of the 5 factors from Owen. Temperature. Another one from Kia. Concentration. Another one from Keita. We got temperature and concentration. Pressure/volume, yes. Another one, Noah? Surface area, yes. And lastly, Matthew. This is the one we haven't talked about much yet. Adding a catalyst, yes. Okay, now out of those five, which one can only work for a heterogeneous reaction? Out of those 5, which one works for only a heterogeneous reaction? That one is what number? 4, surface area.
Water is like homogeneous.
Heterogeneous has 2 or more different areas with different properties. Like a stapler in water, yes. So, if everything is liquid and aqueous, right? If you have water and a bunch of aqueous stuff, that's all one phase, okay? These different areas with different properties are called phases. Now, if I have salt dissolved in water, it's all one phase because it's all the same all throughout. You take a sample from one area, it's going to taste like salt water. You take a sample from a different area, it's going to taste like salt water, okay? Most of the time when you have a heterogeneous reaction, it's going to be between something and a solid. However, you could have a reaction where you have a gas that reacts with something that is in solution. So you could have gas plus aqueous. So if you had a container, and here's your aqueous stuff, and here's your little gas molecules. Let's put a lid on that. Lid. Gas. There is a surface between those two, yes? So you could measure the surface area. Now, what if instead of having that, you had your same beaker, your same aqueous stuff, but instead of having just the gas above the liquid, what if you bubbled the gas in? Bubbles of gas. What does that do to the surface area? So if I have bubbles of gas, but the same volume of gas, would I have more? Same volume of gas, same volume of gas. If those volumes of gas are the same, the total volume, do I have more surface when I just have one blob of gas? Or do I have more surface when I have lots and lots of tiny bubbles of gas? Lots and lots of tiny bubbles of gas. This has a greater surface area. SA for surface area, okay? Greater surface area, and therefore, what would you have more of?
Volume of concentration, no. Collision.
Collisions. Okay, so you have more collisions, and if you have more collisions, what do you have? You have a? Yes, you have more frequency of collisions. What happens to your rate? Your rate is faster. You have a faster rate. No, you're going backwards. More collisions, larger surface area, more means more chance of collisions. So larger frequency of collisions, which then leads to a more successful collisions, which leads to a faster rate. Faster rate is the end result, okay? So that is surface area. All right. Which of these 5 things affects both the frequency of collisions and the percent of collisions which are successful?
Temperature.
Temperature. Affects both. 1, frequency of collisions. This isn't on any page. This is like little review from last week, yes? Frequency of collisions and percent of collisions that are successful. What is the 6th factor that you can't change? Have you guys talked about this one yet? Yes? What is the 6th factor that you can't change, but it will make the reaction, I guess it should say, makes the reaction of rate of one reaction faster than a different reaction? Romina? Nope, that's okay. Ronya? Nope, that's okay. Chloe, where's Chloe? right there. Sorry. The nature of the reactants. And that's what we're going to talk about today. We'll also talk about catalysts. Okay, so catalysts and nature of reactants, we're going to get through that today, and then we'll be done almost section 1.2. And then we'll need a quiz on that, maybe on Friday. Okay. Let's see.
That's making sense. Oh, there's 5 P's. 5 P's. You said there's a total of 12 quizzes.
No, that's an approximation. You guys will have more quizzes than my AP because I split quiz 1 into 2 quizzes because I made them go faster. Okay. All right, we are on page 34. So a catalyst speeds up the reaction by making the energy required for the reaction to occur lower. Okay, so if we were using the analogy of the students bumping into each other and their books flying out of their hands, perhaps it would be like they put mittens on the students so they had a harder time gripping their books. Yes, so the books would fly out more easily, so you would need less energy for the books to fly out. Another analogy is, let's pretend we're at a high jump competition, and if you have a higher bar, it requires more energy to get over the bar. If you have a lower bar, it requires less energy. So out of all the high jumpers in the high jumping competition, which bar is going to have a larger percentage of all the high jumpers who can get over it? A higher percent of jumpers can get over the lower bar. So this lower bar, this one would be like the catalyzed reaction. And this one here would be the uncatalyzed reaction. Does that analogy make sense? Okay. So this one isn't changing the frequency of collisions. It changes the percent of collisions which are successful. So a catalyst does not change the number of collisions. A catalyst changes the percent of collisions which are successful. How does it change the percent which are successful? It lowers the required energy, okay? So, and we say it provides an alternate pathway for the reaction that has a lower required energy. Here's a new word, activation energy. And what does activation energy means? It means required energy. But activation energy is the official term. It's the minimum energy needed for a collision to be successful. Soon we are going to look at potential energy diagrams. Which look like this. The reactants have a particular amount of potential energy just because they've got bonds and things, and any chemical you have has a certain amount of potential energy in it. Products have a different amount of potential energy. And you can see that the reactants in this pathway have the same energy as the reactants in this pathway, the second pathway. The products in the first pathway have the same energy as the products in the second pathway. So this would be the same reaction, just going via different paths. This would be an uncatalyzed reaction. This is our one without the catalyst. And you need to have enough energy to get over that big hill. You can almost think of it as if you were, going hiking. Would everybody be able to get over the big hill? No, I can guarantee you my 82-year-old mom who has 2 replacement hips, 2 replacement knees, and has, had heart problems and has a gallbladder removed, she's not getting over the big hill, okay? She might even have trouble getting over the small hill, okay? But my dad is in remarkable shape for an 82-year-old. He would probably be at least able to get over the small hill, if not the big hill. Yes? So the percentage of people who can get over various hills is going to be different depending on how high the hill is. So the percentage of collisions that will have enough energy to get up there is going to be smaller than the percent of collisions that have a smaller amount of energy. Okay? For now, you can think of the catalyst as a matchmaker, which brings things together. Okay, if these are the 2 things that are going to react, it brings them together and puts them in a position where it's really easy for them to break apart and do something like switch lids. Okay? Did that make any sense? No. Okay. If these are my reactants, activation energy. Yeah. So a catalyst, if I am the catalyst, I take these 2 things and I bring them together, and because they're in the perfect orientation, they don't need as much energy to break apart and then reform the new bonds. Did that make sense? Okay, cool. So those are catalysts. Our final factor, the nature of the reactants. Why does it say 5? That should say 6. I need to fix that. Fix. So the nature of reactants, so far we've looked at ways you could speed up or slow down a reaction. This is only for comparing one reaction with another. Oh, well, that's irritating. I don't have the videos up, but let's take a look at the reactivity of alkali metals in water. Okay, and I'm just going to grab this from here. And this is what, 1.2a. That's not the one I wanted. It's the one down here. So we are going to compare various alkali metals in water.
Here I'm working with some lithium metal, very difficult to cut. I've got a piece of sodium here, pretty easy to cut.
Very quiet.
You notice when I cut through that the fresh sodium is very shiny compared to the rest. Let's zoom in real quick. Let's see if we can really get in there.
Okay, so this is fresh sodium.
So this side will reflect a lot of light. The other sides are pretty dull. And you'll see that especially with the potassium here. I'm going to go ahead and give this kind of a half cut.
And now we've got potassium.
So for the potassium, this is the side that's freshly cut, and you can see the dullness to the other sides compared to that one. So I'm going to go ahead and take those three, and I'm going to add them to water, and we can look at the kind of reactivity of those three alkali metals with water.
So we've got lithium, sodium, potassium.
So here I'm going to take the lithium and add that to the water. It's going to generate hydrogen gas and lithium hydroxide. So you're going to see a pink color develop here, and then you're going to see some smoke come off, and that's either lithium metal or that's lithium hydroxide coming off of there. Maybe a little bit of liquid water. But it's not as reactive as, say, sodium, so I'm going to put sodium into the next one. And the sodium is actually probably going to ignite. So you'll see some orange flame perhaps, or some sparks, or some shrapnel. And then the last one, I'm going to go ahead and put my 2 pieces of potassium in that I've cut in half. So this is less potassium than the other two in terms of amount. But you'll find that the reactivity is a little bit greater.
Okay, so you can see that the reactivity of the potassium is greater than the sodium, which is greater than the lithium. I'm a little bit disappointed we didn't get sparks from the...
Now that potassium there was quite reactive there, but the sodium sometimes will allow hydrogen.
Okay, and just while we're here, we might as well write the reaction for that. So we have, let's pick one of our metals. Okay, come here. Wake up. There we go. So let's take sodium, which is a solid, and we're going to put it together with water, but I'm not going to write it as H2O. We're going to write it as HOH because, and that's a liquid. What type of reaction is this going to be? It's going to be a single replacement reaction. So predict the products of that reaction.
When do we know to write H2 as HOH or H2?
If you're doing a single replacement, it makes it easier to predict the products if you write it as HOH. Okay. If you're balancing if you're balancing an acid-base reaction, that's not a simple one. It can be easier if you write water as HOH to do the balancing, but you never have to. It can just make your life a little bit easier if you do. Okay, so what are our products here? What have we got? We've got NaOH plus H2. That's a gas. That is aqueous. And do we know what type of compound NaOH is? What type of compound is NaOH? That is a base. And bases turn, do you guys know about acid-base indicators? Do you remember them at all? Yeah, if you did a titration last year, you would have used an indicator called phenolphthalein. Phenol, A-L-E-I-N. Phenolphthalein is an indicator. It's an acid-base indicator. And it turns pink in base. And it is colorless in acid. Or neutral. Okay, so you saw that as the reaction went on, you got a pink color because he had placed, that guy had placed some phenolphthalein into the beakers. Do you guys know anything about H2 gas in terms of what happens if you heat it to a high enough temperature? Yeah, it will explode. Explodes when enough heat is around. Explodes with O2 and heat. That's why when we did it with potassium and the reaction rate was very much faster, you got that bang. Okay, that was the bang from the explosion of the H2. Now, where is the oxygen coming from for that explosion? Just from the air. Okay, it's just around in the air. All right. And anything else? We're good. Okay, good stuff. Now, you do not need to know this next part. Okay, you will not need to explain this. Okay, but it tells you why. It tells you what the nature of reactants in this case is. Okay, in this case, as you go from lithium to sodium to potassium, and here is our lithium ion, and here is our potassium ion. This is lithium. This is potassium. What do you notice about the outermost electron? Yeah, this one is much further from the nucleus. Okay, this one is closer to the nucleus. Do you guys know how electrical force works in terms of distance? The farther away, the weaker it is. Okay, it's very much like a magnetic force. So if we had a couple of magnets, they're going to, it's very similar to this. Like if I let go of this magnet here, whoops, that one's backwards. Is it going to work? Oh, no, it doesn't like that one. Okay, hang on. Let me try a different one. Okay. So if I let go of this here, it will actually just attach. But if I let go of it here, the force is not strong enough to overcome the force of gravity. Yes, it has to be a certain distance and then it will snap together. So just like the force, so this is pulled, this electron is pulled to the nucleus with a stronger force. This electron is pulled to the nucleus with a weaker force. Which of those would require more energy to remove that outer electron? More energy to remove the electron. The lithium will require more energy to remove the electron. That means the activation energy for the lithium reaction is higher. So a smaller percentage of reactions will have sufficient energy. So basically, the nature of the reactants affects the activation energy. So that's the only part of this that you need to take away. You don't need to be able to talk about, the shell, how many shells there are, that lithium's shell is further, closer, whatever. You just need to be able to say that the nature of reactants affects the activation energy. So in Chem 12, you're not required to explain the differences. You need to say that the nature of the reactants, affects activation energy. And if it affects activation energy, does it affect the number of collisions or does it affect the percent of collisions which are effective? Percent of collisions which are effective. There we go. Now, there are certain instances that you should be familiar with because these show up in multiple choice questions all the time. Okay? One of those is that if you have a reaction of ions in solution, those tend to be very rapid. What does rapid mean? Fast. So when you have ions in solution, those tend to be fast. So if you're given a list of reactions and only one of them has ions in solution and you're asked which one is fastest, you're going to pick the one that has ions in solution. Now, sometimes this is really easy. You'll be like, oh, look, ions in solution. Yay. Look at me go. I picked that one. That one's really fast. However, you might be given a reaction that looks like this one. And you need to recognize, because you're really good with ionic reactions now, that this reaction involves ions in solution.
Oh, because it's ion.
Because you've got Ba2 plus, 2NO3 minus, just whenever you have time, How can you guys deal with this? This would drive me crazy. There we go.
Oh, wait, it was on center that.
Ba2 plus 2NO3 minus plus 2 Na plus CrO4 2 minus. So you need to be able to look at that and say, I have ionic compounds that are aqueous, therefore I have ions in solution. You can recognize the reactions in formula equations, even if you don't say, oh, look, aqueous ionic compounds. You can recognize them as double replacement reactions. Those are our fastest reactions. Okay, our aqueous ionic compounds in double replacement, those are our fastest. Why? Well, if you've got things in an aqueous solution and you're comparing it to gases, do you remember how far gas particles are from one another? Like super, super far, right? Compared with their size. So what is the likelihood of gases accidentally bumping into one another compared with something that is aqueous where the particles are closer? Less. Yes, so gases are less likely to collide. The other thing to notice is that if you have this, you've got a 2 positive charge and you've got a 2 negative charge. What do negative and positive charges do to one another? They cancel out, but they also do something else. They attract one another. So they don't just have to randomly bump into one another, they will actually pull towards one another even if they just get close, okay? So first thing, particles in aqueous solution are closer together than gaseous, so they collide more frequently. Second, the positive and negative charges attract one another. So they don't have to wait to collide randomly, they are drawn together by that electrostatic attraction. There are other reactions which also involve ions in solution, such as redox reactions, which we will learn about later, okay? But they are not as quick as double replacement reactions. And that's because they very often involve quite complicated collisions. Like, look at this thing. That looks quite complicated, yes? Complicated. So it's going to be slower. Complicated. Slower, but still faster than, say, gases. So these are slower than double replacement, still faster than gas plus gas. Can you guess what state of matter in the reactants would make the reaction the very, very slowest? A solid. Solids make the reaction the slowest. Okay, so anytime you see a solid, you're like, ah, that's the slowest right there. Okay? Solid reactants are much slower. Oh, do we have time to talk about covalent bonds? We do. Okay, phew. All right. So solids are slower because they move much slower, and you need a surface. They're slower moving. Less surface. Now, anything that involves breaking covalent bonds, how do you know that something is going to have covalent bonds? That's a non-metal, non-metals only. So if we look at H2O2, that is a covalent bond. And covalent bonds are very strong. Yes? Covalent bonds are very strong. You should know that. If they are very strong, how much energy do they need to be broken?
A lot.
Yes. Therefore, they require a lot of energy to break.
So that means the reaction will be very small.
That's right. Therefore, the activation energy is high. And therefore, a smaller percent of collisions have sufficient energy to react. And therefore, the rate is slower. Okay. How many of you actually did pages 37 and 38? Actually did it? Good if you did. I know a lot of you were like, I've got a quiz, so I'm not doing that. I'm just going to do the stuff that's related to the quiz. I'm not stupid. So for homework today, if you've not done 37 and 38, could you please do 37 and 38? Some of you have already started working on page 39, and let's tack on 40 and 41. Okay, so 37 to 41. Super fun. And perhaps our quiz for this will be on Thursday. Quiz Thursday.
Oh my God.
I changed my mind.
No. I have a test on Thursday.
You have a test on Thursday? I'll think about it.
We'll see. No, but that's fine.
You have a math thing on Thursday? Okay, I'll make the quiz Friday.
Yay!
I could make it Wednesday instead.
No.
But I like how you think, Alexander.
Yay! Hey.
Don't forget your phone. Thank you.
I'm such a last semester, like, there's so much going on.
It's okay. Are you all right?
Yeah.
Okay.
Slept earlier.
Okay.
Just kept going. And then I wake up.
Yeah. Okay. No worries. No worries. Just let me know if there's anything. Yep.
Come back, question.
Okay. Perfect. Perfect.